Hi everyone, I'm Sara. I'm a PhD student in Télécom at Paris in France, and I'm here to present on my work during my internship in Twitter this summer. So my work consists of comparing word-to-vec and fast text algorithm when linked to Twitter data. So tweets data is a highly variable set of words, mainly because of abbreviations, derivative of abusive words, and sometimes even new words are invented. Which brings us to the problem of which method will allow us to go from this highly noisy textual data to a robust vector representation. So our first comparison task follows 3 steps. We start by building a representative validation set of array words. Then we designed an experiment that evaluated the robustness of the vector representation while at the same time ensure significant statistical bounds of that comparison analysis. So in the experiment, we gathered 7 million tweets as a training data. Then we launched 50 training runs over fast text and word-to-vec algorithms where we fixed all the hyperparameters and we only changed the random seed. This results in 50 embedding matrices for each model, and we use these embedding matrices to build our ranking queries over the 60 validation words. So the first result was with respect to the variation of the cosine similarity between the query words and the set of its most similar words. And what we notice is that fast text is always given high mean and less standard variation than word-to-vec. And we can clearly see that for the word example back with the repeated sequence of A, where we can see that fast text is given a more confident cosine similarity of the similar words than word-to-vec. This variation of the cosine similarity could lead to a variation of the words within the list of similar words. That's why in our second results, we focused on measuring the variability of the set of similar words through the 50 runs using the Jacquard index that will allow us to measure the overlaps of the sets of similar words through the 50 runs. And results show that fast text is 3 times higher, give 3 times higher similarity than word-to-vec. So, but even if the list of the similar words remains the same, the words can change their ranks within this list. So we wanted, in our third result, we wanted to measure the variability with respect to the words rank by measuring the number of words the fast text or word-to-vec algorithm will give to each rank during the 50 runs of training. And here also we saw that fast text is having a less variability for lower ranks than word-to-vec, which tends to have a high variability for all the ranks. So this intrinsic task allows us to conclude that fast text is less sensitive to retraining runs than word-to-vec. But we wanted to confirm that by linking fast text to a downstream task. So we choose toxicity classification because this task is mainly relying on array words. And the architecture of the model classification is a combination of the LSTM layer applied to a sequence of tokens and a dense layer applied to the deterministic user features. The output is a toxicity score ranging from 0 to 1. Our contribution was to replace the embedding layer that uses word-to-vec by fast text embedding layer trained over 500 million tweets containing 2.6 million tokens. I'm sorry for the French representation of 2.6 tokens. And so the evaluation metric is the relative cross-entropy defined as the ratio between the cross-entropy of the toxicity model and the cross-entropy of a baseline model. This metric will allow us to measure how our toxicity model is performing with respect to the baseline one. And here also we saw that fast text leads to 1% improvement of our metric. So that's it. Thank you for listening, and see you at the poster session to answer your question. Thank you.